Have you ever asked yourself a question so simple that it almost feels silly? Why does mass create gravity? Most people think they already know the answer. We learn in school that asterisk mass attracts mass, asterisk big things pull on small things. Planets pull on moons. The Earth pulls on you, which is why you don't float away into space. Simple, right? But here's the uncomfortable truth. That explanation doesn't actually explain anything. It only describes what happens. Not asterisk why asterisk it happens. And once you realize that, the entire idea of gravity starts to feel strange, almost mysterious. Because one of the most familiar forces in your life, the thing keeping your feet on the ground right now, suddenly becomes a giant unanswered question. Why should mass pull on other mass at all? What asterisk mechanism asterisk is doing the pulling? What is actually happening in reality? Before we dig into that mind-bending mystery, I want you to imagine something very ordinary. Picture a train. Not a futuristic bullet train or a sleek metro system. Just a classic steel train rolling along a set of steel rails somewhere in the countryside. You can almost hear it, the steady clanking rhythm, the vibration of metal against metal, the enormous weight of the locomotive pressing down onto the tracks as it moves forward. Now think about something most people believe they understand about trains. Why don't they fall off the rails? If you've ever looked closely at train wheels, you might remember a small detail. Each wheel has a little lip on the inside edge, a raised ridge called an asterisk flange. Asterisk. Most people assume that this flange is what keeps the train from slipping sideways and falling off the track. It makes intuitive sense. The rail sits between the two flanges, and if the train starts drifting to one side, that flange bumps against the rail and stops it, like a guardrail. That's the common explanation. And if you ask 10 people how trains stay on their tracks, chances are most of them will give you exactly that answer. The flanges keep the train from falling off. But here's the surprising part. That explanation isn't really true. Or at least, it's not the full story. In fact, if the flanges were the asterisk-only asterisk thing keeping trains on the rails, trains would derail far more often than they actually do. Because those flanges are not designed to constantly rub against the rails. They're more like emergency backups. Most of the time, they aren't even touching the track at all, which raises an interesting question. If the flanges aren't holding the train in place most of the time, then what is? What invisible rule is quietly guiding thousands of tons of steel along two thin lines of metal with astonishing stability? The answer turns out to be surprisingly elegant. And once you understand it, something strange happens. You start realizing that the explanation you believed at first, the obvious one, was only a surface-level description. A convenient story that helped things make sense quickly but didn't capture the deeper mechanism underneath. And that brings us back to gravity, because the way most people think about gravity is a lot like the way people think about train wheels. We're given a simple explanation early in life: mass attracts mass, objects pull on each other, planets pull on stars, stars pull on galaxies, the Earth pulls on you. But if you stop and think about it for even a moment, that explanation starts to feel incomplete. How does the Earth, asterisk, reach out asterisk and pull on you? What is doing the pulling? Is there some invisible rope connecting every object in the universe? Is there some hidden force traveling between them? Or is something even stranger happening? For hundreds of years, the greatest minds in science have wrestled with that question. From Isaac Newton staring at falling apples, to Albert Einstein reimagining the very shape of space and time itself. Each step brought us closer to understanding gravity, but each answer also revealed something deeper and more unsettling about the nature of reality. Because the true explanation for why mass creates gravity isn't just about force, it's about the structure of the universe itself. And once you see it, once you truly understand what's happening beneath the surface, the world stops looking solid and predictable, space stops behaving like empty nothingness, and gravity stops being just a force pulling things together. Instead, it becomes something far more bizarre, something that quietly reshapes the way you think about reality itself. But before we reveal that answer, we need to go back to those train tracks, because the hidden reason trains stay on the rails will help you understand the hidden reason planets stay in orbit. And the connection between those two ideas is far more surprising than you might expect. At first glance, the flange explanation feels perfectly logical. In fact, it feels so obvious that most people never question it. Think about how our brains naturally picture the situation. You imagine the train wheels sitting on top of the rails like two long steel lines stretching into the distance. The train moves forward, the wheels spinning smoothly as the massive weight of the locomotive presses down. Now in your mind, Zoom in closer. Look at one wheel. You notice that little raised ridge on the inside edge, the flange. It sticks out slightly like a tiny wall built into the wheel, and suddenly the whole system seems to make sense. If the train drifts to the left flange bumps into the rail and stops it. If the train drifts to the right flange bumps into the rail and pushes it back, just like the bumpers in a bowling lane. The ball rolls down the lane, and if it starts drifting too far to one side, it taps the bumper and gets nudged back toward the center. So naturally, people imagine train wheels working the same way. The rails are the lane, the flanges are the bumpers, and the train is the bowling ball rolling forward, constantly being kept in line by those little metal edges. It's such a satisfying explanation because it matches something we already understand. Our brains love familiar patterns, and this one fits perfectly into a mental picture we can easily visualize. But let's make that picture even clearer. Imagine you're standing right beside the tracks as a freight train approaches. You hear it before you see it, the deep rumble echoing through the ground. Then the locomotive appears, massive and heavy, pulling dozens of cars behind it. Each steel wheel spins rapidly as it rolls along the rails. Now imagine shrinking down until you're the size of a coin, standing right next to one of those wheels. You watch it spin. You watch the rail slide beneath it. You expect to see the flange constantly brushing against the side of the rail, guiding the wheel like a guardrail. But something strange happens. The flange isn't touching the rail. In fact, there's a small gap between them. The wheel is rolling smoothly along the rail, but it's not being held in place by that raised edge. The flange is just sitting there, not doing anything most of the time. That's odd, because if the train were really relying on the flange to stay on track, you'd expect constant contact, metal scraping metal, tiny corrections happening every moment as the train tries to wander left or right. But that's not what engineers observe. Most of the time the flanges don't touch the rails at all, which raises a slightly uncomfortable question. If the flanges aren't guiding the train, then what is? How does something weighing thousands of tons manage to stay balanced on two narrow strips of steel for miles and miles without constantly hitting those edges? At this point, your intuition might start trying to fill in the gaps. Maybe the train is just heavy enough that it naturally stays in place. Maybe friction keeps it centered. Maybe the wheels simply roll straight. But none of those explanations fully solve the puzzle, because trains don't always travel in perfect straight lines. They go around curves. They shift slightly left and right as they move. Wind pushes against them. Tracks bend and flex. And yet somehow the system remains incredibly stable. It's almost as if the wheels are quietly correcting themselves. Almost as if something in the design is gently guiding the train back toward the center whenever it drifts. But if the flanges aren't doing that job, then something else must be. And here's where the story becomes interesting. Because the real reason trains stay on the rails isn't obvious when you first look at them. You have to notice a tiny detail that most people completely overlook, a detail hiding in plain sight. If you examine a train wheel closely, not just from the side but from the front, you'll notice that the surface touching the rail isn't perfectly flat. It's slightly angled. The wheel isn't shaped like a simple cylinder. It's more like a very gentle cone. That subtle shape changes everything, because it means the wheel behaves very differently depending on where it sits on the rail. And once you realize that, the motion of the train starts to reveal a hidden self-correcting mechanism, one that keeps the train centered without the flanges needing to touch the rails most of the time. But the deeper reason this matters isn't just about trains, it's about the way our brains accept explanations. We often settle for the first answer that asterisk sounds asterisk reasonable. The first story that feels intuitive. The flange explanation feels right in the same way the old explanation of gravity once felt right. Mass attracts mass. Objects pull on each other. Simple. Comfortable. Easy to imagine. But just like the train wheel story, that explanation might not be the full picture. Because when scientists began asking deeper questions about gravity, the same way engineers examine train wheels more carefully, they discovered something surprising. Something hidden beneath the surface. And just like the true design of train wheels, the real explanation for gravity turns out to be far more elegant and far more strange than the simple story most of us grow up believing. So if the flanges aren't constantly guiding the train, what actually keeps it centered on the rails, the answer hides in a detail so subtle that most people never notice it. Train wheels are not perfectly cylindrical, they're slightly conical. That means the surface that touches the rail isn't flat like a soda can rolling on a table. Instead, the wheel is shaped like a very gentle cone, wider on one side and narrower on the other. At first glance, this seems like a tiny design choice, but it creates one of the most elegant self-correcting systems in engineering. Let's picture how it works. Imagine a perfectly cylindrical wheel rolling on a flat surface. No matter where that wheel sits, the diameter touching the ground is always the same. So if the wheel drifts slightly to one side, nothing changes. The left side and right side still travel the same distance with each rotation. There's no reason for the wheel to correct itself. Now imagine something different. Instead of a cylinder, picture a very shallow cone. One side has a slightly larger diameter while the other side has a slightly smaller diameter This small difference changes everything. Because when a wheel with different diameters rolls, the larger side wants to travel farther with each rotation than the smaller side, and that creates a natural steering effect. To see this clearly, try a simple thought experiment. Imagine holding two rubber bands stretched between your hands. Now imagine that one rubber band is slightly longer than the other. If you tried to move both forward together, the longer one would naturally pull ahead. The system would start turning toward the shorter side. Something similar happens with train wheels. When the train is perfectly centered on the rails, both wheels on the axle rest at the same position on their conical surfaces. That means both sides have the same effective diameter, touching the rails. So both wheels roll forward at exactly the same speed. Everything stays balanced. But now imagine the train drifting slightly to the right. It's only a tiny movement, maybe a few millimeters. But because the wheel surface is conical, that shift changes where each wheel touches the rail. The right wheel moves toward the narrower part, of its cone. The left wheel moves toward the wider part, Now something fascinating happens. The left wheel suddenly has a larger effective diameter, while the right wheel has a smaller one, And remember what we said earlier, a larger diameter wheel travels farther with each rotation. So the left wheel tries to roll slightly farther than the right one, but the two wheels are fixed together on the same axle. They can't rotate at different speeds. So instead of one wheel moving faster, the entire axle gently turns. And which direction does it turn? Back toward the center of the track, without any electronics, without sensors, without constant friction from the flanges. The geometry of the wheels quietly guides the train back into alignment. It's a passive, self-correcting system built entirely from shape and motion. The moment the train drifts off-center, the wheel diameters become uneven. That unevenness causes a natural steering effect, and the train smoothly slides back toward the middle of the rails. Then once it reaches the center again, both wheels return to equal diameters. The steering effect disappears. Balance is restored. All of this happens continuously as the train moves. Small adjustments happening automatically, thousands of times per minute. The flanges are still important, of course. They're like the emergency guardrails. If something extreme happens, a sharp curve, track irregularities, or sudden sideways motion, the flange will contact the rail and prevent the wheel from slipping off. But under normal conditions, the train almost never relies on them. Instead, the conical shape of the wheels quietly does the real work. And once you understand this design, something interesting happens. You realize the original explanation, the one most people believe, wasn't completely wrong. The flanges, help keep the train on the rails. But they're not the true mechanism, they're just the visible backup. The deeper explanation lies in the geometry of the wheels and the way motion responds to tiny differences in diameter. It's a beautiful piece of engineering, simple, elegant, and almost invisible unless you know what to look for. But here's where things get really interesting, because the way we misunderstand train wheels is strangely similar to the way we misunderstand gravity. For centuries, people believed gravity worked like a kind of invisible pull, objects reaching out across space and tugging on one another. Just like the flange story, that explanation seemed perfectly reasonable. It matched our intuition, it gave us a mental picture we could easily imagine. But as scientists kept asking deeper questions, they began noticing gaps in the story. Tiny inconsistencies, strange behaviors that didn't quite fit the simple idea of objects pulling on each other through empty space. And eventually those questions led to a realization that was just as surprising as discovering the conical shape of train wheels. Gravity wasn't really a pulling force at all. Instead, something far more mysterious was happening, something woven into the very structure of space itself. And once you see that hidden mechanism, the universe begins to look very different. Now step back for a moment and think about what just happened. We started with something incredibly ordinary, a train rolling down a pair of steel rails. Most of us thought we understood how it worked. The explanation seemed obvious. The little flanges on the wheels stopped the train from falling off the track. Simple, logical, end of story. But the moment we looked closer, the story changed. Those flanges weren't actually doing the main job at all. The real mechanism was hidden in something much subtler, the asterisk shape of the wheels themselves. Asterisk, a gentle cone, almost invisible to the eye, quietly creating a self-correcting system that keeps thousands of tons of steel centered on two narrow rails. And that tiny discovery reveals something much bigger about how the universe works. Because physics is full of explanations that look simple on the surface, but hide deeper mechanisms underneath. The first explanation we hear is often just the asterisk starting point, not the full story. Think about how many everyday things we interact with without ever questioning them. Doors open when we push them, balls fall when we drop them, light turns on when we flip a switch. These things feel so familiar that our brains label them as understood, even if we've never actually asked asterisk how asterisk or asterisk why asterisk they work. But when scientists investigate these ordinary experiences, they often discover something extraordinary hiding beneath them. Take electricity. For most of human history, electricity was a complete mystery. You rubbed amber with cloth and somehow it attracted dust. Lightning flashed across the sky with terrifying power. People saw the effects, but the underlying mechanism remained hidden. Then over centuries, scientists uncovered the deeper layers: electric charge, fields, currents, electromagnetic waves, and suddenly the everyday act of turning on a light switch became part of a vast invisible system of electrons moving through circuits. Or think about sound. When you speak, it feels like your voice simply travels through the air. But in reality, your vocal cords create tiny pressure waves that ripple outward through billions of air molecules, bouncing, compressing, expanding, carrying information through space until they reach someone else's ears. What feels like a simple experience is actually a symphony of physics happening all around you. Even something as basic as walking involves an incredible chain of hidden principles. Friction between your shoes and the ground, muscle contractions powered by chemical energy, balance systems in your inner ear, constantly correcting your posture. The deeper you look, the more you realize something astonishing. The world is far more asterisk intelligent in its design, than it first appears. Not necessarily intelligent in the sense of a conscious designer, but elegant in the way physical laws create systems that regulate themselves. Train wheels guiding themselves back to the center, planets maintaining stable orbits around stars, atoms forming stable structures that allow matter to exist at all. Nature often solves complex problems with surprisingly simple rules. And once you learn to look for those hidden rules, everyday objects start to feel different. Take the train example again. The next time you stand near a railway track and watch a train pass by, you might notice things you never thought about before. The enormous weight of the cars, the precision of the steel rails stretching into the distance, the quiet geometry of the wheels touching the track. You might remember that tiny conical shape, the detail most people never notice, silently guiding the train back toward the center again and again. A small piece of engineering that reflects a deeper idea. Asterisk. Motion can correct itself when the geometry is designed carefully enough. Asterisk. That realization changes how you see the system. And this way of thinking is exactly what scientists use when they study the universe. They don't just accept the first explanation that sounds reasonable. They keep asking questions. If something works, why, does it work? If a pattern appears, what deeper rule is creating that pattern? If a simple story explains the surface, what mechanism lies underneath it? This mindset is what led Isaac Newton to rethink falling objects. Before Newton, people simply accepted that things fall to the ground because that's their natural place. Newton wasn't satisfied with that answer. He asked a deeper question. What force is causing the fall? That question led to the law of gravity. But the story didn't end there. Centuries later, Albert Einstein looked at Newton's explanation and asked another question. What actually causes that gravitational force? And his answer completely changed our understanding of reality. Gravity wasn't just a mysterious pulling force. It was the result of mass bending the very fabric of space and time. Planets weren't being pulled through empty space. They were following the curves created by massive objects, just like train wheels follow the subtle geometry of the rails. A deeper structure guiding motion, a hidden shape influencing the path of things that move. And that idea brings us back to the bigger lesson hidden inside our simple train story. The world is full of explanations that feel obvious, but obvious explanations are often only the asterisk surface layer, asterisk. Real understanding comes from curiosity, from being willing to question things that seem settled. Why does this work? What mechanism is actually responsible? What hidden structure might be shaping what we see? When you start thinking this way, ordinary life becomes full of tiny scientific mysteries waiting to be explored. The curve of a bicycle tire, the way birds glide through the air, the way water spirals down a drain, even the way shadows stretch and shrink during the day. Each one is a doorway into deeper laws of nature, and sometimes the most fascinating discoveries begin with the simplest question. A question like, why doesn't the train fall off the track? At first it seems like a trivial curiosity. But follow the answer far enough and you start learning about geometry, motion, engineering, and the quiet elegance of physical laws. And that's the real beauty of science. It doesn't just give us facts. It teaches us asterisk, how to look at the world, asterisk, to see hidden systems where others see ordinary objects, to notice patterns where others see randomness, to ask questions where others stop wondering. So the next time you see something familiar, a train on its rails, a ball rolling across the ground, or even the simple act of something falling, take a moment to pause, look a little closer, because beneath that ordinary moment, there might be a surprising principle, quietly shaping reality, a small detail, hiding a big idea, and once you start noticing those hidden ideas, you'll never look at the world the same way again.